reset your brain on the problem. We need to allocate 5 million to these 3 plants, and all of them gave number of proposals, how they spend money. So C is the money part, R is the revenue part. In return for giving them the money, they promise certain revenue generation. Okay? So the idea is to maximize the revenue, right? If you don't spend the money, it's lost. Now there are 24 different possibilities. If you look at the table, okay, 3 plants, 4 proposals, cost and revenue model, so 24 వస్తుంది అక్కడ. So we take it at face value, right? And then there are certain infeasible proposals, so we eliminate them. Okay, and then you have obviously which are very bad proposals, like for example this one, like proposal 1, 1 and 2 returns only 4 million. The goal is to maximize the revenue. Okay, now why we don't want to do total enumeration other than for toy problems? Because the problem set or the sample space is going to be humongous, right? It's a no-brainer. Okay, by now you have learnt enough computer science stuff in your classes, you know that enumeration doesn't work for these large and complex problems. Okay? How do you find out if something is infeasible? Again, there is no set rule. While you are working on it, you will figure it out. Okay, these things lead to inefficiency. Okay, so these are all some of the reasons. Chakravarti, I don't think these people have learned linear programming yet, right? In any of the classes. You can put it in chat. I don't think they learned that. So let's not worry about linear programming in this class. Yeah, Chakravarti. Okay. They have not learned. Okay. Now, here is the author, whoever gave this example. Here is one way of calculating the solution. Okay. So the problem is broken down into 3 stages. Okay. And each stage represents the money allocated to a single plant. Okay, that means you are taking 1 plant at a time. So in this case, stage 1 represents the money allocated to plant 1. Okay, so you are taking plant 1 first, you are allocating some money. Then stage 2 is the money to plant 2, and stage 3 is the money to plant 3. Okay. And you have to pick some order in which you do the stages, and in this case they just took 1, 2 and 3. Okay. Now the second concept is each stage is then divided into states. That is the dynamic behavior of every plant in this case, right? So what does the state comprise of? It's nothing but it encompasses the information required to go from one stage to the next stage. So in this case, remember we talk about finite state machines in one of your classes, introductory classes. You have states and you have transitions. So here the transitions are from stage 1, which is plant 1, to stage 2, plant 2, and from there to plant 3 and so on. Okay, so look at the nice way. I actually liked it. I did not really pay too much attention to all the details, but a couple of things I highlight for you. So you can see here the state, the values that are applicable on plant 1 could be anywhere 0, 1, 2, 3, 4, 5. The same thing happens here. Okay, plant 1 and 2, right? How did you come up with these things? It's quite simple arithmetic, right? If you spend all the money, initially you're considering stage 1, plant 1, you have all the money, right? So you can give the plant 0 money or 1 million or 2 million or 3 or 4 or 5. So once you allocate something to plant 1, then when you take 1 and 2 together, what would be the resulting set, right? Again, you will have full state space potentially, right? Okay. Now, after you do that, the goal is when it's time to allocate. See, ultimately you have to allocate some money, right? Without allocation, the revenue would be 0, right? So ultimately, by the time you come to stage 3, you do know that between all 3 of the stages, you would have spent all $5 million. Because if you leave money on the table, that's lost. Okay. Now, associated with each of these stages is a revenue. Okay. So now this is the important point here. To make a decision at stage 3, we only need to know how much was spent in stage 1 and 2, right? If I spent 3 million, I know how much money is remaining for stage 3. If I spent all 5 million, I know I will have zero money. Okay? So capture all that. The way to capture all that is the table here. Okay? So this is stage 1 table. Okay? Stage 1, plant 1, if it gets 0, okay, then what is the optimal proposal? Okay? Then they get 0 value, right? So if you allocate 1, then you see what proposal is optimal, and then you can see the revenue, right? Depending on how much you allocate. Got it? Is there anyone who does not understand this table here? I can explain it in a little bit more detail, right? So it looks basically, the thing is, if I allocate 0, then what is the proposal that can be considered? And if you go back here, proposal 1 annadu. So allocation 0, right? Proposal 1, right? Revenue would be 0. Okay. Now if you allocate 1, then it is proposal 2, because plant 1 gave that, right? So if you go here into the table, no magic there. See that? 1 million into proposal 2 key, and then the revenue that they promised is 5 million. So all you're doing is converting that into a slightly different format of a table. Okay, so now once we do that, so we are done with stage 1. Now we are going to go to stage 2. Stage 2 is what? Plant 2, right? So now we have to figure out what is the best solution between, because plant 1 is done, right? So now we have to see, combining with plant 2, what is the best solution. Okay? So we go through all the plant 2 proposals, allocate the given amount of funds to plant 2, and use the above table to see how plant 1 will spend the remainder. So you're taking the data information for both the plants together. That is what you're doing there. Okay? So once you do that, you do the permutations and combinations, right? Simple arithmetic or permutations combination that we learned. If I give 1 million to plant 1, then I'm left with 4 million for plant 2. If I give 2 million to plant 1, then I'm left with 3 million to plant 2. And these are the revenues. So you add them up like that. Okay? Okay. So now out of these things, you can see that based on the algorithm that is there here, proposal 1 for plant 2 and proposal 2 for plant 2 are returning 14. So there are 2 14, so you can choose one of them, right? 2 and 3. Okay. Got it? So once you fill that out, then you go to, you fill out a similar table here. Okay? Then we go to stage 3. Okay. That means whatever has been allocated for 1 and 2, it's done. Only remaining would be there. Now again you go through all the proposals here, see the amount of money remaining, and use table 3 to decide the value of the previous stages. Okay. So you are kind of applying some concepts of recursion here, right? Okay. So once you do that and add up those things, you get some net value here. Then you will see that proposal 2 gives revenue 4. Okay, leaves 4. Okay, so that is the optimal solution there. Okay. Now remember, I used the word recursion. So you are in a sense doing that, right? You are keeping track of the previous state. You are recursively going back and updating the table there. Okay. So stage 2 calculations are based on stage 1, and stage 3 only on stage 2. Okay. Okay. So that is what is also known as the principle of optimality. I kind of defined some of these things in the first lecture on dynamic programming. You can go review the slides. Okay. Now, nothing is easy in programming. In case you're saying, oh my god, this is so confusing, if professor gives an exam question, would I be able to do it? Well, if you know the fundamentals, you should be able to do it, right? The fundamentals here is the concept of stages and the concept of allocating something in stage 1 and using the data in calculating stage 2 values. And once you're done with stage 2 and stage 3, then you use the output of stage 2 in computing the values of stage 3. So that is the algorithmic flow for that. Now, is this a problem that we encounter in the industry? We encounter this every quarter in Cisco or any company, because all the VPs and all of these people have money, right? And all the groups, then they have to submit proposals to these VPs, say, hey, if you give me this much money, I'm going to generate this much money in the quarter. Okay. Now the VPs have to have some way of number crunching all of these things. So if you're a hotshot data science engineer, you would be able to do something like this. I mean, that is the theory, okay? In the reality, I do not know how well these things are done in the industry. Okay. So much for that. And if you have any questions on that, by the way, I will post this solution in the community. And students, I would like you to kind of work in teams offline to understand that algorithm, apply that to the capital budget problem, and verify that you do get the answer 80 there. In the process, you are learning to think too. Okay. Now, where am I here with respect to? Let me share my slides here. Am I sharing my slides? Not yet, right? I don't know why I'm sharing Jabber. Okay, I'm sharing my here now. So I just gave you the solution there in the slide. When I post the updated slides in the community, you can download it. Okay. Optimal binary search tree. This is for today. If you finish early, you can go home early, right? But we'll see. Remains to be seen. So why do we talk about optimal search tree? What is the motivation for that? Right? So we already know search trees, right? When we have binary search trees, we already know, like we go to the root. Whenever I have a search key, I go to the root. I either follow the left subtree or the right subtree, right? Depending on what the value I'm looking for. Okay. Now, most often in applications, what happens is, what we are searching for is kind of like known. It's called the domain knowledge. Okay. Like for example, if I am doing a payroll application, right? I know what type of searches I would be doing in a payroll application, right? Like, what does the boss make? What does an engineer make? So I kind of know whose things I'm tracking more closely. So I already know the search keys. That's prerequisite. To do the optimal binary search tree, that's a prerequisite. Because you kind of know what type of searches you perform. And the frequency of the searches. Now, in the situation that binary ago, we build called optimal. Okay? Now what is optimal there? Because here we kind of know what we are looking for most of the time. Okay? So now in your mind you should be thinking. It's an optimal binary search tree saying, aha, going to search at the branches level. Right to the optimal binary search. Questions, student? Okay. Important. We typically use these things where after the basic tree, because if you do insertions, remember there are some examples in the community too. When you do some insertions, the tree can be uprooted, right? It can change, so it doesn't work in those situations optimally. When the tree is built in steady state, then this algorithm and this tree make sense. Okay, so you have an example of a tree here. Follow this carefully. I'll repeat it a couple of times. The tree, you all understand it, and then because next slide I think you will be doing some work. So you have a tree there, right? You all agree that it's a binary tree, right? At most, no brainer. Okay. Now you see this thing here called key frequency. So what is this key frequency? What it says is precisely what I explained in the previous slide. I said, you know how frequently this is, meaning the search can happen. So here the algorithm are ATD, and then what it says is, hey, A is the frequency of accessing C is 1, and so on. Okay, so there is a table given to you saying, hey, these are the searches that I do most frequently, and this is the frequency. Okay, now you are a programmer. Okay, you are asked to say, hey, I know what my search pattern is. I want you to build a tree, and what is the goal there? You want to minimize the cost of accessing all the nodes. If you were to search all those nodes, what would be the total cost? Okay, you understand the problem? Is there anyone who does not understand the problem? I'll repeat it. Please feel free to ask your faculty members to put it in chat. If you get lost in this slide, you will get lost rest of the lecture today. So super important to get this slide right. Okay, I should look at the participants' faces. If they don't talk, I can also figure out from the body language. Okay, show of hands, Jntuk. Do you understand this slide? What I just said? If you understand, raise your hands very high like that. Okay, I see only a few hands raised. Let me explain one more time. Do a show of hands again, okay? So when do we use optimal binary search? Do we want to build? We already know how to build. All of us know how to build trees, right? And we into that we also have additional information. Additional information from the problem domain says I lost the video from me and others. Reached along the videos. The additional information says, you know what? I know I search different values in tree. Why by tree? Because it's such a value. Otherwise, there would not be a value search. I also know frequency with which I search for different parts, different values. Not everything would be searched every single time. Google search for Telugu Sim. For most of, I can't see even a single video, Andy. Did you turn off? You don't know what to show me your pretty faces, enthusiastic faces. Turn off the video because something is coming there. So who do you search for most often? Put something in the chat. Come on, students, don't feel bad. You'll most often search for Samantha, right? Is she the hotshot girl now, or is it really Kajal? Some one of those. Now, if you're a girl, you'll probably put something. I think it's most often we search for Mahesh Babu or Junior NTR, right? Or Shahrukh. So always some bias for the searches. That is what this is saying. And then typically you are given that frequency table. Now here I put a hard-coded value. Okay. Now I get the image back of the NTV. So here for convenience I put a hard-coded value, but most often when you get deeper and deeper into the subject area, you get into probability density functions and so on, right? Everything would be based on probability functions. Okay, but for convenience I put hard-coded values here. Okay. Let me ask Chakravarti garu. Chakravarti garu, meeku ardhamainda ee slide? See, I'm asking a faculty member. You can put yes or no. Okay, got it. So I'm sure Chakravarti garu understands that, right? So now what is the goal when I know the search? Why are we harping on saying, okay, what the deal about knowing the frequencies? Because as a programmer, your goal is to minimize the cost of accessing all the nodes. If you were to access all the nodes, because for every action this is going sense. So what we are saying is in this example is we are assuming 18 searches. Okay, why we are assuming 18 searches here to go there? Yeah, somebody put there SVCW to everyone. Fantastic, Andy. Okay. Now 18 ekkadi nunchi vachindi manaku akkada. If you add up this 4 plus 2 plus 1 plus 3 plus 5 plus 2 plus 1, that is 18. Students, see that 18 match 18 there. Okay. Now you are computing the steps basically, right? What does this 1 star 1 mean here? So you're computing the total cost. Okay, that means I want to traverse the full tree, right? So if you look carefully here, that to access C, what is the cost of the search? 1, right? Because it's the root node, correct? Now C occurs from the frequency table 1. So you have 1 star 1 corresponds to how many search steps plus, multiplied by the frequency. 1 star 1 here corresponds to C. You got it? Okay. Now, let's see. I think they have bandwidth issue. That's why I'm not able to see all the videos yet, other than Chakravarti garu. But you can try turning on your video. Other colleges. Okay. So 2 star 4. 2 star 4 ekkadi nunchi vachindi manaki, because you are navigating to the left subtree here, A, right? So to access A, to search A, you're basically taking two steps, right? One is checking with, is it equal to that? You stop. If not, then you go based on this. And the put together. 2. Now, how many times A is occurring? Do more and then the total cost of the steps equal to how much, Andy? Somewhere I think it's 42 or something like that, if I am not mistaken. You can verify that. Okay. Now I know that. How do I verify that you understood it? I am going to give you a group exercise now, right? That's the fun part. So let me see what is the group exercise I'm giving. Nothing, slide didn't come there. Okay. So what I am asking you to do, faculty members, please help me out there to facilitate the group interaction there. I want you to rearrange the tree to reduce the total cost. Okay. How do we do that? You may want to write it down here somewhere. My notes slow. Students, open your notepads, paper, pencil, and write down these things, and then I'll put the previous slide back. So I gave you a tree. The cost of that is, I think, whatever the cost is. I did not calculate that. You do all the 1 star, 1 plus all of those things, you will know some number. Okay. Now, if you were to give values A, B, C, D, E, F, G with those frequencies, you have to rearrange them in such a way. In this case, I am saying using greedy method. Now, what is the greedy method here? Greedy method is always highest value they take. Remember, coins avani chesam manam. We did a lot of examples on greedy method, right? So here, what is the greedy method? You insert the nodes in a BST in decreasing order of frequencies. Until you start with the highest frequency, you insert that first. Then you go to the next highest frequency, you insert that, and so on. I'm getting static. Let me mute you for a second. Can you mute yourself? Somebody is giving a lot of static here. Let me mute. MIET, I muted you to see if static, yeah, it gone away. So, do you all understand the problem that you're trying to solve here? What I'm saying is we have this tree. Frequency and this is how somehow, let's say, some programmer who didn't know data structures and algorithms, they constructed a tree like this. Okay, it is taking forever for the customer. The customer now comes and tells you, hey, can you somehow opt a tree for me? Because the searches are taking too long. Okay. That's a very common problem, by the way. Search algorithms are the most complicated. Okay. A lot of graph theoretic principles are involved in coming up with efficient search algorithms, and that continues to still develop, right? Okay. So what is the cost of this one to minimize the cost of accessing all the nodes? If you add this one, 1 plus 8, 9, plus 4, 13, plus 6, 19, plus 9, 28, 28 plus 3, 31, plus 20. 31 plus 20, 51. So minimum cost equal to 51 actually. Okay. Your goal is to rearrange these things by using a greedy algorithm, and when you rearrange it using greedy algorithm, you will get an F cost, whatever is the total cost. So I want you to do that and tell me what is the cost. Okay. Is there anyone who does not understand the problem? Faculty members, do you all understand what I'm asking for? So that way when your students ask you in class, you can help them what I'm asking. Okay? And you can also put it in the chat. Okay, so time now is 9:54 and 15 minutes. Vasavi, not Vasavi, it was, who gave the answer first? It was SVECW, right? SVECW. I will make you the presenter. You can share your tree and the cost. Oh, somebody got 38. Wow. You are better than me. Okay. So this is nice. I'm glad you all exercise your brain power trying to do that. Let's see. Before I show the next slide, how about I pass the ball to SVECW for a little bit of bragging rights by them. And I'll making you presenter, Andy. SVECW, I made you the presenter. So by doing that, if you have your tree on a laptop or something, you can actually show it to us. If not, you can project it onto the screen and then we can see whatever works for you. You can have one of your students present the tree to us, or you can write it on the whiteboard. Yeah, that should be fine too. Okay, let's all pay attention to SVECW. By the way, I don't want anyone of you to be thinking it's a waste of time. This is a way of learning from each other, and we should be appreciative that somebody is presenting, okay? Go ahead, Chairman. You can open a new whiteboard if you want, or you can. Chairman.
Your root is Ii Sem.
Root is E now. Okay.
Right.
Let me try to draw the picture.
Yes, sir.
No problem. I can do it for you. Let me take the ball away from you then, and then I can do it for you. Okay? Give me a second. Give me 1 second. Let me take the ball away from you, but I will write it for you. So you're saying root is E. Oh, I couldn't see your screen there, but let me do it. Okay, root is E. Okay, then
Root is E, sir, and its LSP is P, sir. Its left subtree left
okay,
P, sir. Its left node is B.
B as in boy.
Yes, sir. B is boy. Bombay.
Okay, got it.
B is for Bihar.
Okay. Okay. Next.
And its right node is F.
Okay. B ki right node.
Yes, E. E right node is F.
Okay,
E, sir.
got it.
E right node is F.
Got it. Got it. Give me a second. Is what F for?
F for fast.
Okay, got it. Next.
And P left node is A and the right node is C.
Okay, B ki left node is A na?
B left node is A and right node is C.
C for cat.
Yes, sir. C for cat.
Okay.
And C right node is D.
ఇంకా ఉన్నాయి ఇంకా కొన్ని లెటర్స్ ఉన్నాయి కదా.
Yes, sir. Again, C right node is D and then F right node is G.
F right node is
G.
C.
G, sir. G.
G. Okay, got it. G for God. Okay. Okay, A, B, C, D, E, F, G antena.
Yes, sir.
And the cost is కొంచెం గట్టిగా చెప్పండి, మిస్ అయిపోయాను. 40
sir. Its cost is 43.
43. Okay, thank you. I think we should all give them a nice big clap, okay, because they participated. That's good. Okay, that's what I want from my students. Excellent. Now let me ask others about some of the other answers. How many of you agree with this answer? There is at least one fight you will have because JNTU V has something else. So this is what they came up with. Now JNTU V came up with an algorithm which shows 38. Okay. Let's see what I have. I didn't pay. Let me check mine. Okay. Okay, how do you compare this with the thing there? This is what I got based on the greedy method. So if I go back to the whiteboard that you have, am I sharing my screen? Okay, you have E, B, E, F, G, D. Okay, you have E, B, A, C, D. Okay. Okay, so let me share my screen now. Somewhere I'm not able to share. Let me close the whiteboard. I should be able to share my screen. Okay, application Microsoft PowerPoint. Okay. చేస్తే నాకు ఇది ఇలా వచ్చింది. When I did it, I got 42. Slight EFG same as what you have, whereas here instead of, I think in your case you went from E to B, whereas I had E, A, D, B, C. I think this somewhere here it flipped. So that needs to be verified. But what is interesting is JNTV got 38. Can you share JNTV, the thing that you got 38? Can you share, put it in the community for us, please? So I want one of your students to go put your 38 solution in the community, so that way all of us can look at it and comment on it. I can take a bet that you have some mistake somewhere, but if you win, I'll give you $10. Whoever got the lunch. Any questions from others? From the rest of the gang? Chakravarti garu meeku ఏమైనా questions ఉన్నాయండి? Let me, okay, SVCW is good. JNTUV, please put it in there. And then Mandava, do you have any questions? Or Vasavi? Anyone? Okay, perfect, no questions. Student, did you like the exercise? Show of hands SVCW. I can see your picture, that's why. Is it fun? Good. Now, do you want more? Okay. Yeah, you will get more too, don't worry. Okay, now let's move on with the lecture. And I'm trying to get some tea, but I'll wait. I'll skip the tea. Okay. Is this the next slide? Okay. So what we basically did was, we came up with some algorithm. One second. Okay. So I'm basically putting it in words. How did we do that, right? So some text here. What we did intuitively is what the theory is. Okay. So remember we said it's all about bottom-up solution, right? So you take small problems and get the answers, and then we don't have to recompute again. Okay. So how did you do this? How did SVCW or JNTUV or other colleges do it? You take all the nodes in a bucket, and then you create one tree consists of one node. Okay. And the cost of the tree is just the frequency of access to the root, right? So we know that. So what was the very first node that you took? You took E, right? Because it had was it E which had the frequency of 5? Whichever node. Okay. Okay, then what do you do? Then you take two nodes, K1 and K2. So, and how do you take those two nodes? You're always taking based on the frequencies, right? So then you do K1 and K2, K2 and K3, Kn minus 1 and Kn. Do you see the number of pairs that are there? How many pairs we get about? If you have 3 numbers, the pairs that you get is what? N minus 1 pairs, right? Right? Behind the scenes, that is what is happening. I wanted you to know that. Okay. Now after you do that, then you consider trees with 3 nodes. So you're slowly building up the tree. 1 node, 2 node, 3 nodes, etc. Right? So once you compute those costs, you're saving those costs in an array. Okay, so that way you don't have to recompute them. When you are analyzing other subtrees, you already have the value for this one, so you plug it in. So that's the algorithm that we use to build that tree. Now, That is dynamic programming. Okay. Now, what you did in greedy method was you always took the highest frequency, right? You always took the highest frequency because greedy is all about the taking the largest and then going from there, right? So by applying this algorithm here that I showed you, right? Now it's easier said than done. It's very easy for me to put it in a slide deck here, okay? Now imagine writing a program doing these 4 bullets. I mean, that is what distinguishes a great programmer from an average Joe, right? Okay. So by applying these techniques, what are we doing? We're taking one node at a time. Then we take pairs, then we take triplets, and so on. Then we come up with an optimal binary search tree. Okay. Now in the previous example that I showed you using the greedy method, my value was 42. Okay. But by applying this bottoms-up approach, I came up with a tree which looks slightly different, and then the cost is 1 less. Now again, I am discounting what Jntuk has done. I would be very interested in knowing how they came up with 38. That is quite possible. Remember, why is it possible? For the sake of argument, let's assume what they have done is right. Why is it that is possible compared to what I have here? That goes back to what we learned in the previous class, didn't we? Remember when we had that coin example of 13? It depends on how you divide it that leads to the optimization, right? When we divided it into 7 and 6, there was one answer. When we divided it into some other combination, there was another answer. So maybe they applied a perfect breakdown that gave them that answer of 38. So convince yourself how to get to this 41 by applying the principles of dynamic programming, where you're doing a bottom-up approach. Okay? So I'll leave that as a food for thought for you after the class. Okay? I don't know about the students there. I remember when we were students, I can tell you these are the type of things that would make us stay awake all night long to solve them. Because if you go to bed without solving them, you cannot sleep. We get so excited, right? Hopefully you will have that same excitement to solve this. 41 seems to be the right, most optimal solution. Okay? Okay. Let me go to the next slide. Now for those of you who are geeks who are into programming, here is one good programming algorithm that I found to solve the problem. The intent is not to teach you how to program here, okay? It is there. You can go convince. There are some nice good comments here, and you can go there and try to execute them. The more you do it on your own, the more you learn, right? But you can see here, this guy, whoever came up with the algorithm, he came up with the number of binary trees that he constructed is n times n plus 1 by 2. Okay? But the theory of binary search trees of n nodes is you can come up with 2n factorial divided by n plus 1, n factorial raised to 2, blah blah blah, right? You can see how efficient this guy came up with the algorithm to do that, to come up with that solution. Reduce the computational complexity drastically. Because there is no factorial. Remember, factorials are most expensive. Okay. Now, at the undergraduate level, quite honestly, I don't really expect you to understand this level of detail. I don't know how your exams are, but if your teacher expects you to remember this level of detail, then they are not doing justice to it. Okay, so that's the algorithm. What do I have here? I have a problem. I don't know what problem I put there. Let me check. So now the next few slides basically shows some theoretical discussion. What I did, if you by now you know the modus operandi, right? I always make you do a practical problem to give you insights. Then I put some theory there. So we'll kind of go through this set of slides. Okay. The theory is for optimal binary search trees, given a sequence of sorted keys, and each of these keys have a probability pi for every key, right? That is the key table, remember? You want to build a binary search tree with minimum expected search cost. That is the problem statement. Okay? And depending on the cost is equivalent to number of items examined. We know that. Now you can see here, how do you compute the cost? I gave you an example. We just put it in theory here, right? The cost is basically depth. At what depth that key is plus 1. Okay? Because plus 1 always comes because of the root. Okay? That's why you get that cost. Now this is also a legitimate question, by the way. I can give you a tree there. I can give you that frequency, and I can ask you to come up with this fourth bullet here. Put it in the form of an equation to compute the cost of a key at the depth t. What is the value? So you should be able to seamlessly come up with that. So there's some, I'm not going to go through this level of math here, okay? But I just put it there. For those of you who are math oriented, you can convince yourself that the sigma and depth, all of these things, blah, 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 would add up. All the sigmas that you do see here, this is equivalent to the equation that I showed you. Remember 1 star 1, 2 star 3 and all that stuff? All of those things is what this equation captures. Okay. Now let me go to the next slide here. Okay. So here is an example. Must be familiar to you, right? You can see here he has given the depths and he has given the probability. Okay, and the search cost is 2.15 for this. You at a given depth, right? The reason why you get 2.15 is you add plus 1, remember? So 1.15 plus 1 is the 2.15. Okay, that's how it came up. He came up with the number. Those are all the probabilities. The table is built and you come up with the search cost. Okay, what do I have here? So there is another way of coming up with the same thing, and you can see the search cost came to 2.10, different type of tree, right? I made you do 2 types of trees, remember? So by doing it same thing here, it came a search cost, and then turns out this is the most optimal. Okay. So what are the observations that we make here? Number 1, the optimal binary search tree may not have the smallest height. If you notice that one, the height increased significantly, right? If you see your first tree which I showed you and the second tree which you came up with as an exercise, you can see the difference in height. Okay, and you can make that observation. Number 2, you can also make the other observation. May not have the highest probability key at root. In greedy, you will have the highest probability key at root. Whereas in optimal BST dynamic programming based one, you will not necessarily have the highest probability key at the root. These are 2 important observations for optimal binary search trees. Okay. There's some theory there. Some big omega number. You can see if you get into more details, you can see the order of that there, right? Different BSTs with n nodes. What is the order? He's showing you that one. I'm skipping the optimal substructure because we kind of covered it in a couple of previous classes, so for now I'm skipping it. If you guys want to know something more about it, I'll be happy to delve into that a little bit more next class. Because when you have a subtree, all it is saying is, when you have a subtree of a binary search tree, it contains key in a continuous range. Okay, and then it's a standard proof technique, right? So, but this is not a proving class, so I'll skip that. So I just had some additional slides. So don't be alarmed when I show some additional slides like that which are there, which I skip through. When I take notes, I always have a lot of additional stuff like that. I may or may not necessarily cover it in the class. Okay. So this one I was not intending to cover, so I'm going to skip it because it's very theoretical. There are some slides that I have to skip, sorry. Since I'm in a presentation mode, I have to go through that. Okay, this is all related to that. Big proof. Okay. So, how do we do it algorithmically? Remember I told you whenever we have these subproblems, we store the search cost in an array, right? Array could be a two-dimensional array, then it becomes a table. Okay. Again, all this would be totally nonsensical for you at this point. Too theoretical, right? And I gave you some algorithm there. We kind of browsed through this last class, if I remember. Okay. Let me summarize it here. So whenever you have to do dynamic programming, this we covered in the very first class, Introduction to Dynamic Programming. When I say first class, I mean first class related to this chapter. Okay. So the focus is on coming up with that optimal substructure, right? How do you divide up the problem that way it lends itself to an optimal solution? And then there's overlapping subproblems. I gave you the example of factorial, for example. Right? Whenever you have factorial, when you go down, it's always like you keep computing the same, like n minus 1 factorial, n minus 2, and so on. So whenever you have that kind of an overlap, you compute the solution once and save it in a table, so that way you don't have to spend time again trying to compute that. And then the way you show that there is an optimal substructure is use the principle of recursion. Okay, when you make a choice, then remember the coin example again. You made a choice of dividing up 7 and 6, right? And then you will have those subproblems to solve. So you recursively solve the subproblems once, save it in a table, and then when you combine the solutions together, you will get an optimal solution. We gave some examples there. You just have to go look at the initial set of slides. So there are some. Okay, that's it. I think I have for. There are some questions. I'm sorry, I'm skipping some of these things because I was lazy to delete them. Okay, here are some things, right? I think we had some proof. I remember vaguely that I said, hey, A implies B does not mean B implies A, right? That applies to dynamic programming. So go back and review those slides, the initial set of slides where I discussed this one. This was some. And then we gave this example too. When we talked about all shortest path, remember I said when we apply the dynamic programming, we were able to come up with the shortest path. But the longest simple path we could not come up with because there was a cycle there. If you recall a small cycle diagram that I gave, I said, hey, dynamic programming doesn't always work. And that particular illustration shows when you have a cycle in a path, this longest simple path cannot be solved using dynamic programming. And the justification for that is, like in the case of shortest path, they are all independent subproblems, whereas in the longest path, they are not independent. That's a simple answer for that. Okay. Independent longest simple path. It's in one of the very first slides in the same slide deck. You have that cycle there. There are two paths going from node A to node C, I think, and one of the paths is shorter than the other path. So that's what we prove in that particular example. Okay. Okay, it says botanical. Yeah, okay. By the way, those slides that I skipped, don't worry too much about them because they are all superfluous slides. Okay, questions, comments? Okay, no questions. Wow. Okay. Again, in case you're wondering why I skipped, as I told you, there is no need to really get into that level of detail in this type of a class. Good. So as I told you, I'll finish early today. I can discuss anything else that you want me to discuss in the remaining time to answer your questions. Here is your time for the next 20 minutes to ask me anything that you want. Exam preparation or any topic, because I want to get into the traveling salesman problem and the knapsack problem next class. Okay, why don't I give you some assignment? Anyone else answered that question or not? But I posted this notes there in the community, so this should give you very clear answers as to how, when you have a B tree, how to insert and delete values. So whichever student posted that, apply the steps that I have given in this particular document and see if you are able to do it. It's pretty straightforward. If you still have questions, please send me the email and I'll be happy to walk you through that. Okay. That is one thing that I wanted to share with you. This is again a very legitimate question, deleting and inserting values in a B tree. Okay. If I were you, I would pay close attention to the notes that I posted there and review that. Okay. What else I need to share with you? I was looking for some file that I wanted to share, but that one. Let me see if I can find it. Give me one more second. Introduction. I'm trying to. I was trying to look for traveling salesman problem to set you up for next class. Yeah, this is the one. Okay. Do you see my screen? Okay. I think I'm sharing my screen, right? So next class, what we'll do is, besides knapsack, we'll also be getting into this traveling salesman's problem. So I want you to do some Google search and try to understand it. I'll just set the stage here for you today, and then next time when we meet, we can go into the depth, right? So as you can see here, the goal is to visit a number of cities in the minimum distance. Okay. So here is a table that it gives you where you're traveling from New York to Miami, Dallas, Chicago, and coming back. Okay. So how do you solve this one? This is very similar to, if you see this one here, real problem is solving this to define the stages, states, and decisions. Now what does that should ring a bell in your mind, right? That is very similar to what we did in that budget allocation. Remember, we had the concept of stages, states, and then we made decisions. Stage 1, stage 2, stage 3. Very similar concept is applied to the traveling salesman problem, as you can see here, right? So that is one way of one way of solving that, right? Now the problem is, you can see here as it says here, the state space here is so large, it becomes impossible to solve. Okay? Let's say if you have 20 cities, how would you solve it? You can see the why dynamic programming becomes so easy, it's so important, right? You can see the numbers here, they are horrendous. If you have 100 cities and you're trying to do that one, you can see here, the 50th stage shows this number. Do you know what this number even is? Anything beyond 5 or 6 zeros to me is infinity. Okay? So, how do you solve these types of problems using dynamic programming is a big challenge. That is what we'll be focusing on in the next class. Okay? So, just look up some two things. Assignment for the students basically is, I'll write it here on the board. I'll say stop sharing and then I'll open it in the whiteboard and do a new whiteboard. Okay. Give me a second. So this is what I want students to do. One, look up. We covered knapsack problem, remember? The traditional knapsack problem. And try to understand the now in greedy, what did we do in the knapsack problem? You know that, right? When the thief goes there, he always picks up the highest value first, right? Because the bag has a limited capacity, he picks up the highest value. Okay? That's not necessarily the most optimal. And we are going to apply dynamic programming to come up with the optimal solution. Okay? I want the other given time. Good. Traveling salesman problem. Okay? So these are the two that I want you to look up. And then when you look up, right, you simply cannot come and say, oh, we looked up, I'm done. Okay? You have to basically tell me in the community, post your thoughts about these problems in the community. Okay? So, I want you to start explaining stuff. If you have any questions on that, start putting questions there. Then rest of the students who have looked up these things, they'll say, hey, I found this great resource, this is how you should understand it, whatever the case may be, right? I want some interaction between now and Wednesday on these two things in the community. Everyone understands that? Fair enough? It's a two-way street, right? I want you to teach me. How about that? So you are doing these things so that way you can teach me and your other faculty members how these things are done. Okay. Any more questions? Faculty members, do you want to add any more, Randy, to what we discussed? It's an open mic here. I am done talking. I am done preaching. It's not just talking, right? Members, please feel free to add your thoughts there to any of these things. Okay, if not anything, then I am done for the day, a little bit early today. Every time I'm keeping you 10 minutes longer, today I'm leaving you 10 minutes sooner. And thank you SVCW for your participation. Chappan, you're trying to talk?
I think we have hardly 7 days only, sir. Sir,
7 days. March
Only-
19th kada.
yes, sir. March 19th is the last working day, but during this we have only 7 days. That is 7 into 14 hours we have.
Yeah. That should be good for us to cover the other modules.
Syllabus now we are in dynamic programming. In that again you are mentioning these 2 points. I think knapsack problem, traveling salesforce problem, and then all-fair shortest path problem is also there. These are pending in.
All shortest path man already covered this.
Yeah, it was yesterday.
Yeah.
Then
Even
next
knapsack also we. Go ahead.
Backtracking and branch and bounding, so many problems are there. They will take more time, sir. Is it will be covered during this all 7 days, sir?
It will be covered. Remember, we have to do one extra class too. Remember that?
Okay.
Because remember, I missed one class because family was sick. We had to
Yes, sir.
schedule
Yes.
one more class. Yeah.
Yes, sir. Yes, sir. Yes, sir.
Yeah.
That is
We
true,
are
sir.
fine. Yeah.
Yes, sir.
I am not worried about that because that's why I said hey, we have enough time, and then I should be able to cover those.
Yes, sir. And one more thing, today morning we were started with a capital budgeting problem, but which is not there in our JNTK syllabus, sir. But even though it is good, sir.
It is not about only. It is not. That's a good point. It is not about a capital budget problem. It is about dynamic programming. Okay. Yeah, because I have to take different examples from a practical perspective to instill in them how dynamic programming is done. Okay. If you want my honest opinion, your JNTU syllabus, I'm not a big fan of that syllabus, right? But having said that, I still have to prepare them for the test, right? Classes here when they do, my students do a lot of programming exercises, right? But the way the JNTU syllabus says, it constrains me in doing that, right?
Yes. Yes, sir. We are very
but
fascinated.
don't-
Yes, sir. But thing is,
No.
we are afraid about the JNTK syllabus. Questions is coming from that. The students also feeling that is expressing their feeling towards.
Oh, absolutely. But the good thing is I'm going to give them a cheat sheet. Like remember how before the midterm I gave them a full summary?
Yes, sir.
I will do the same thing for the final two for them. See, my philosophy is very simple. I don't prepare students for test. I don't teach to test thing. Okay? I teach them so that way they acquire practical skills where they will do well when they go into the industry, right? But at the same time I balance. See, ultimately they have to all pass, right? So I'll give them enough shortcuts and examples for them to do well on the tests. So not to worry.
Yes, sir. Thank you, sir. Thank you for giving us the valuable information. Thank you.
Okay. Great. Anything else, Andy? Okay, so that's why you see it's a two-way street, right? For example, I ask the students to go look up these examples, right? So they have to do their part in sincerely going and looking them up and then posting them in the community, right? Their understanding. It's really a two-way street here, okay? They have to do their part too. Okay? Great. Anything else?